All right. Hey, everyone. I guess we can go ahead and get started. Yeah, how's everyone doing? Hopefully, hopefully good. Thanks, guys. Cool. So I guess we're gonna go ahead and get started. So yes, as always, we have our homework assignment that's due tomorrow. If you have any questions, feel free to pop by. And yeah, I think what I'd like to do is I'd like to set a goal for myself to, at the very least, post your project specifications by next Friday. So that is, fingers crossed, that is a goal that I'm setting for myself. When I post those project specifications, I think what I will also do is post some sort of a Google spreadsheet, which can give you guys the opportunity to look for group members if you don't know anybody in the class. Also, I would say, can also post on Piazza if you're looking for group members. And then, like I mentioned, I will reserve about 10 slots, if you will, for those of you who really want to work by yourselves. And, the main reason for that is, usually what I tend to reserve that for is for students who have a data set that, that is like their own personal data set that they're working on for research, and they'd really like to focus on that. So that's why I sort of reserve the opportunity for some people to work on the project by themselves. But, unfortunately, I teach 200 students in one of my classes, and there's, I think, about 70 students in this class. So, grading that many individual projects is not something that I have the time and the resources to do, unfortunately. So most of you will have to work with other people. So I'll post opportunities for you to meet with people if you don't know anyone in the class. Cool. So stay tuned for information on that. Yeah, and today what we're going to do is wrap up with our discussion on principal component analysis. So we're going to talk about a few additional things that principal component analysis can do for us. And again, the primary goals that we're pursuing with PCA in this class is for learning purposes. So in particular, how can we unlock hidden insights in our data set with principal component analysis? Or in other words, how can we learn more about the data set that we actually have in our hands? And then after that, I think, if we have time, which we should, we'll move on to Unit 12, which is going to be talking about non-negative matrix factorization. Now, the cool thing about non-negative matrix factorization is that it can actually be used jointly as both a clustering algorithm as well as a dimensionality reduction algorithm. So it both gives you the ability to cluster the observations in your data set, as well as learn more, basically represent your data set in a smaller number of dimensions while still preserving some aspect of the original data set. Okay, so basically NMF will be our third dimensionality reduction algorithm that we've talked about in the class. And again, so we've talked about TS&E, we've talked about PCA, and we're also going to talk about NMF. So again, you always want to remember, the thing that distinguishes dimensionality reduction algorithms from each other is the aspect of the original data set that we are trying to preserve. So just as a review, what about the original data set are we trying to preserve with principal component analysis? A question for y'all. So is it the clustering structure? Is it something else? Yeah, exactly. So in PCA, our goal is to preserve as much of the original attribute variance sum as possible. Now, in TS&E, our goal is, more implicitly to preserve the clustering structure of the data set. And we do that by preserving the pairwise neighbor relationships of the original data set. So that's something to think about. And I wanted to focus on that distinction as well, because often, usually when I'm teaching in person at the very least, I have a lot of students that come up to me at this point in time and they ask me, well, is it okay for me? So let's just say I have a high dimensional data set and it's, too computationally burdensome to, run in some of the traditional clustering algorithms that we've talked about. So I've had a lot of students come up and ask me, they say, well, can we take our data set, our original data set, and can we instead choose to cluster the principal components of that data set such that, our clustering algorithms run a little bit faster. And my answer to that is always, well, it depends, right? So you want to remember, principal component analysis is not explicitly attempting to preserve the clustering structure. It's only attempting to preserve the total attribute variance. So what that means is that in some scenarios, you might actually have a very strong clustering structure in the original data set. But if you choose to project your data set onto a set of principal components, sometimes that clustering structure can actually weaken or disappear altogether. So that's essentially what we're going to end up seeing in our MNIST dataset. So this kind of showcases, among many other things, why we need to be careful when it comes to using principal component analysis in our clustering algorithms in particular. All right, so we'll talk more about that in just a second. So there's a couple of additional things that I wanted to talk about more conceptually when it comes to principal component analysis before we get to our final application with the MNIST data set. So this is bear with me here for 1 second. Yeah, so this is talking about something that we touched on Tuesday, in which we can actually use what we call the inverse transform. So basically we can transform, or we can initially transform our original data set X with our P loading vectors. And then basically, hold on 1 second. And therefore, this gives us a lower dimensional representation of our original data set X with simply P dimensions. Now, if we wanted to take our set of principal components and we wanted to reproject those P, or basically reproject that P dimensional data set back into the same n dimensional space that X existed in, then what we discussed, or what we can do, is we can take our loading vectors matrix, i.e. our U matrix, and we can transpose it. So basically by transposing that, we get a P by N matrix. Basically, we can use that transposed loading vectors matrix U transpose and get a transformed version of our original matrix X. I'm going to call this, actually, let me call this X bar, or X hat, excuse me. Okay. So basically what this does is it takes our original matrix X. So basically this transformation here gives us the P principal components of X. Okay, so basically this transformation, the original transformation, it projects our original X matrix onto simply just the first P principal components. So basically this is a set of information that has been, extracted, if you will, or preserved, with this projection. And then basically by only taking what information was preserved with these P principal components, we can, again, multiply that loading vectors matrix that has been transposed and get a version of the original matrix X, which has only preserved that which was projected onto the first P principal components. So the question is this new matrix X hat, is it guaranteed to be the same as the original matrix X? And the answer is no, not necessarily. And specifically, if the number of principal components that you're using is less than n, you will not actually end up getting the same matrix. Okay, it's simply just going to be the representation of X that has just preserved only that was projected onto the first P principal components. Okay. So we might think about, well, why is this useful? Why might we be interested in, taking our original matrix, projecting it onto just P principal components, and then representing it in the same n-dimensional space. So basically by completing this inverse transform. Well, there's actually a variety of reasons for why we might want to do this. So for instance, it might be the case that your data set has a certain degree of noise represented in that X matrix. So by projecting your data set onto just a smaller number of principal components, P, the things that you're actually preserving with those P principal components might in fact actually be the main sources of variability in your data set. Or in other words, for instance, if we're looking at the MNIST data set, what we might expect to see is the main source of variability to be, the pixels that are different based on, what digit you're actually drawing. Now, provided that the amount of noise in your data set is relatively small, we would expect the noisiness, so it's like the noise showing up in the background of the image, for instance, we might expect for that variability to be comparatively a lot smaller. So, if we're trying to preserve, the relationships or the pixel relationships that capture the most amount of variability in the data set, what we might expect to see is that those first P principal components are going to be preserving, what makes a digit, like a 0 digit, look different than a 2 digit. And then furthermore, we might expect, some of the additional principal components, i.e. the principal components that we're not actually keeping, to reflect more of the noise. So by taking, our original matrix X and reprojecting it into a different version of X, which has extracted some of the variability, it could be a way of essentially cleaning out some of the noise that may have existed in that particular data set or in our images. So we could use it as one such method for cleaning noise from, or noise variance from a given data set. Okay. Any questions on that? And then another useful reason for why we might, for instance, first calculate just P principal components of a matrix X and then reproject it back into an n-dimensional data set is for the purpose of, for instance, image compression. So for instance, let's just say there's two sets of people that would like to send and receive image data, like the MNIST data set. So let's just say you have you, and let's just say you have your friend. So let's just say you and your friend both started with some original data set X. Okay, and then you found a certain set of P loading vectors that correspond to the covariance matrix of that X matrix. Okay. And then you use that loading vector matrix U to create your corresponding P principal components. Or in other words, a different, right, smaller dimensional representation of your original matrix X. Okay. Now let's just say, for instance, both you and your friend, you feel okay with this training data set that was used to create this U matrix. So both you and your friend keep that loading vectors matrix U. Okay. Now, let's just say, for instance, I have another data set. So I have another data set of images. Let's call this X bar. And let's just say this has another set of images, which each also have n dimensions or n pixels, if you will. So if I wanted to, for instance, send the most important elements of this new matrix X to my friend, while only, essentially while like if I wanted to send a much smaller version of this matrix to my friend, which therefore might be more efficient, if I wanted to send this to them, then what I could do is I could take this new matrix, X bar, multiply it by the same loading vector matrix U, and then I could get a smaller dimensional representation of that new matrix, so Y bar. So the nice thing about that is rather than having to send this huge X bar matrix to my friend, which may take a lot of time, a lot of computational resources, instead what I can do is I can simply just send this set of principal components that correspond to this large high dimensional data set X. And then all my friend needs to do in order to represent that set of principal components back in n-dimensional space, all that he needs to do is simply just take that loading vectors matrix U, transpose it, and then he ends up getting another version of my original matrix X bar that most likely is not going to be the exact same version of my original X bar, but most likely if I've chosen enough principal components to project this matrix onto, most likely the key information or the key source of variability that creates distinction in these images will in fact be preserved. So the nice thing is basically it allows for me to represent an original data set on a much smaller dimensional version, which allows for me to more easily send the most important parts of the original information to another person. Okay, so that can be one additional reason why principal component analysis can be useful. Okay, questions on that? Okay, and I want to discuss some additional assumptions for when principal component analysis tends to be the most useful. Okay, so number one, it tends to be the most useful when the variables that you have in your original data set are in fact numerical. Okay. Now, another useful assumption is that the relationship that exists between your variables, or basically all of the pairwise relationships that exist between your variables, is in fact linear. And the reason why is, essentially what we're doing is we're asking ourselves, when we're creating this principal components analysis projection, is, we're asking ourselves, well, what is the vector which represents a linear relationship? What is the vector that captures the most amount of variance that exists in this original data set? So for instance, if we're dealing with a nonlinear relationship between a set of points like this, then coming up with a vector that captures the most amount of variance in this data set is not going to be the most effective way at actually, describing the relationship that, captures the most amount of variance. Ideally, we'd be able to say, well, what is the line, if you will, that captures the most amount of variance that exists in this data set here? However, principal component analysis assumes that the relationship, if you will, or the line that we are projecting these points onto, or the curve that we're projecting these points onto, is in fact a line. So therefore, the summarization ability, I guess you could say, of a principal component analysis tends to be most effective when the relationship that exists between your variables is linear as opposed to nonlinear. And so furthermore, principal component analysis tends to be the most effective when you're not dealing with any significant outliers. So for instance, if you're trying to describe, if you're trying to find the relationship that, captures the most amount of variability in a given data set, well, if you had a data set that looks like this, the most informative relationship, or the most informative vector that describes, essentially the relationship that exists between the observations in this data set would be a vector that is moving in this direction. However, if you ended up having just a single outlier in this particular scenario, well, then the vector that is going to capture the most amount of variance in your data set is probably going to look more like this. So when it comes to actually using these loading vectors to interpret, the highest amount of variability that exists in your data set, this, interpreting this vector here is not going to be as insightful when it comes to actually describing, the key relationships that actually exist in this data set, which is going to, be more effectively modeled with a vector that looks like this, essentially. Okay. So someone's asking the question, why would the friend in the scenario not be able to use U inverse to get the exact copy back? So basically this only ends up being the case when, so basically the only time in which you can get the exact copy back is when U has N loading vectors. And the reason why is the following. So let's just say we, rather than using P loading vectors in our U matrix, let's just say we are now using N loading vectors in our U matrix. And therefore, if we multiply our N principal components by U transpose, there's also an N by N matrix, then essentially what we're doing here is we are simply just multiplying U in N by matrix, an N by N matrix times another N by N matrix here. And based on the properties that we described when it comes to multiplying U by U, we end up getting the identity matrix. Okay. So let's just see here. Okay, so basically this is the only scenario in which this will actually end up giving us an exact representation of the same thing back. I think what I might do in the interest of time, because I am running a little bit low on time here, I might come back to this question as to why this actually doesn't work out when the number of vectors in U is smaller than N. But yeah, this actually takes a little bit of a lengthy proof to go through. So we can kind of discuss that at the end of class if you'd like. Okay. All right. And finally, principal component analysis tends to produce more reliable results when you have large enough sample sizes, if you will. So generally speaking, a rule of thumb that we end up seeing that tends to be effective at giving us more reliable results is generally when you have at least 150 samples or 150 observations. And in particular, you have at least 5 to 10 basically observations for every attribute that you have in your data set. Okay. All right. So these are just some additional assumptions about when using principal component analysis can be useful. So after this, we're going to go to our MNIST dataset application. But any other questions before we move on? Okay. All right. So let's go to our final exercise. Okay. And so, we've seen the MNIST data set before. So we use fuzzy C-means on this data set to learn more about the the clustering relationship that inherently exists in this MNIST data set. So given that given that we know that a data set has a clustering relationship, performing cluster analysis on this data set, or, for instance, using the TS&E algorithm to represent the clustering structure of this data set, can, produce useful insights to, tell us a little bit more about that clustering structure. However, it might also be useful for a given data set to explore, for instance, what attribute relationships characterize the highest amount of image variability that exists in this data set. It might also be useful, for exploratory data analysis purposes to, ask the question, what attribute or pixel relationships characterize the second most amount of variance of the digits that exist in this data set, so on and so forth. And so also we might be curious to know, how many principal components is considered to be enough to sufficiently capture a high enough amount of that original attribute variance from the original data set. And furthermore, we can use what we have learned about these pixel relationships. So basically the relationships described in our first, second, third, so on and so forth, loading vectors. And then we can use the corresponding principal component values for a given observation to learn a little bit more about what might summarize each of those observations in that data set. So, this can be really, using principal component analysis on an image data set can be really useful if you want to explore very quickly, if you quickly want to summarize what are the key sources of variability that might exist in your given data set, and basically how to go about summarizing each of your observations based on those key sources of variability. So we've already imported the MNIST data set before, so we're not going to really go into that again. Now, for performing principal component analysis, what you might choose to do ahead of time is you might choose to mean scale the data set. Now, we're going to be using the PCA function in this analysis. So what that means is that, technically, we did not need to mean scale the data set ourselves first, because the PCA function will automatically do that for us, which is nice. However, what we're going to see, given that we'd actually like to visualize some of our inverse transformed images, what we're going to see is that we're actually going to we're going to want to keep the original means of our data set around in order to enable us to, get more accurate representations of what those reprojected images actually look like. So before we mean scale our X data set, what I'm going to do first is I'm going to calculate each of the column means. So basically each of the 64 pixel means of the observations in our data set. And I'm going to save this mean list around. So basically this is the mean of the first pixel. This is the mean of the second pixel, so on and so forth. So I'm going to keep this because I will need this later. Okay. Now, given the fact that I'm actually not going to directly just go right into using PCA, I'd actually like to use the more manual way of calculating my principal components first. I am actually going to mean scale this data set manually. So again, if I'd like to simply just mean scale a data set, I will use this same standard scalar function as I've used before, but I'm explicitly going to tell it to not scale with the standard deviation, or in other words, do not divide each of my observations by the column standard deviation. So I'm simply just creating my mean scaled data set here. Okay, and I can in fact check that the new means of each of my 64 columns are 0, so that is what I would want. And so we're actually going to use this transformation a little bit later with our reprojected versions of our X data set. So if you've ever liked to take a mean scaled data set and add the corresponding column means back, you can simply just take that mean scale data set and simply just add those column means. So you end up getting the same original matrix that you had before. Okay. And so before performing more sophisticated descriptive analytics techniques on our X matrix, it's always a good idea to perform more basic descriptive analytics techniques. So again, you want to remember that the thing that we're actually trying to preserve in this analysis is the sum of our mean scaled attribute variances. So in other words, we want to preserve in our P principal components as much as we can of this 0.0018 original attribute variance. Or in other words, we'd like the sum of our P principal component variances to be as close as possible as this number here. Okay, so before performing principal component analysis, I'd like to ask myself, well, do I actually need all of the 64 possible principal components that I could use with principal component analysis? So to give myself a sense as to how many principal components I actually need, I might actually decide to do the more manual calculation of my principal component analysis. So what I might do first is calculate, again, the covariance matrix of my mean scaled data set X. And again, I do need to transpose it in order to give me a covariance matrix, which is basically 64 by 64 dimensions. Okay, so this is my covariance matrix here. And I can take that covariance matrix like I've seen in the previous analysis and calculate the corresponding eigenvalues as well as eigenvectors of that covariance matrix. Okay. Now in this case, we aren't necessarily guaranteed to have all of our eigenvalues in descending order, which is what we need. So if you'd ever like to sort a set of values in a NumPy array in descending order, you can use the NP sort, and then you can basically use this index operator. So basically the -1 essentially says take the sorted eigenvalues and basically the NP sort will automatically sort your values in ascending order. So basically by using this value here, it reverts the order. So basically it reverses the order that you originally had here. Okay, so this gives me my eigenvalues of the covariance matrix in descending order. Now you want to remember that I want to compose or arrange the corresponding covariance matrix eigenvectors in that same sorted order, the same order in which I sorted the eigenvalues. So what I can do is essentially perform the same operation. So sort the eigenvalues and then basically reverse the order. But now what I'm doing here is I'm using the arg sort. So basically what the arg sort does is it first sorts a NumPy array in a particular order. And then the arg part of the arg sort, what that does is it'll essentially tell you the original index of the value that has been placed first in the sort order. It'll give you the original index of the value that has been placed second in the sort order. So basically this gives me the corresponding order that I would like to sort my eigenvectors by. Okay, so this basically allows for me to arrange my eigenvectors in the corresponding order, or the order that corresponds to the corresponding eigenvalues that have been sorted in descending order. Okay, so by arranging those eigenvectors in this order, the sort order that I just stipulated, this gives me the appropriate loading vector or set of loading vectors that I would want to use for my principal analysis. Okay. And so, for the purpose of this, preliminary analysis to determine how many principal components I actually want, I'm actually not necessarily going to be using these loading vectors by themselves, but more so what I'd like to explore is how do the eigenvalues of my covariance matrix, what essentially do they tell me? So again, you want to remember that the eigenvalues of your covariance matrix, when you've placed them in descending order, what they correspond to is the variance of the first principal component, the variance of the second principal component, the third principal component, so on and so forth. So we might, and again, if we were to add up all of these principal component variances for all 64 principal components, then we know that those principal component variance sums should in fact add up to the sum of the variances of our original attributes. So we might want to ask ourselves, well, what percent of original attribute variance are we okay with preserving, essentially? Or what is the minimum amount of original attribute variance that we would like to preserve? So one way that we might figure that out is we can cumulatively add up these eigenvalues, or in other words, cumulatively add up the variances of each of the corresponding principal components. And then we can divide by the sum of each of those eigenvalues or principal component variances. So what this tells me is that if I were to use simply just one principal component in my Y matrix, then I would be preserving 14.9% of the original total attribute variance. What this tells me is if I were to use just the first two principal components, I would be preserving 28.5% of my total original attribute variance, so on and so forth. So I might decide to plot the cumulative variance sums that I would get if I were to use the corresponding number of principal components. And then, based on my particular research goals, I can use this to determine, well, how many principal components is enough to preserve the amount of original principal component variance that I'd like to. So for instance, you might have some sort of preconceived threshold in mind. So for instance, you might say, at the very least, I'd like to preserve 80% of original attribute variance with as low or as a small a number of principal components as possible. So you might have this threshold, this preconceived threshold in mind. Alternatively, what some people do is they'll look for a point of diminishing returns as we increase the number of principal components. So you can see here as we move on to the 16th principal component, or in other words, the principal component with index 15, we might say, well, okay, at this point, well, roughly this point, we're reaching this, if we were to add one more additional principal component, the amount of increase to the, saved or the preserved original attribute variance is not all that much. So we might decide that preserving 16 principal components might be the best, combination of keeping a high enough amount of principal or amount of original variance while keeping the amount of principal components that you're using, relatively small. And so I can see that, if I were to use 16 principal components, then cumulatively I'm preserving 84.9% of the original attribute variance. Okay. Any questions on that? Okay, so with that preliminary analysis in mind, we might decide to actually move on and use the actual principal component analysis function. And using those insights, I will choose to use just 16 principal components. And again, unless you have stipulated that you would like to use the more basic, you know, deterministic version of calculating those principal components. It is a good idea to stipulate a random state because the PCA function will actually use non-deterministic heuristic functions on the back end to help you more quickly calculate those loading vectors, essentially. So once we do that, we get our PCA object. Okay, and when we're ready, we can use the fit transform function on that object with either our mean scaled or our non-mean scaled MNIST data set, because again, the PCA function will perform that mean scaling on the back end. And so when we use the fit transform function on the PCA object that we've created, what that gives us is our P principal components in our matrix Y. Okay. And so for instance, we might be curious to see, what does, what kind of results might we end up getting if we examine those, 16 principal components that we have calculated for each of the observations in our data set. Okay, now, given that this is an image data set, we might be tempted to say, well, okay, we started with a 16, or excuse me, an 8x8, pixelated grid that we represented these images by. And it just so happens that we got lucky and we selected this, the 16-dimensional representation of X, which, technically could be reshaped into a 4x4 image. So if we decided to do that, then, we're not really going to see anything super insightful here. So the key thing that we want to remember is that, when we project a image data set onto a lower dimensional set of principal components, it's not quite as easy to interpret, these principal components as actual images. So the principal components themselves don't actually represent any insightful images, if you will. However, if we wanted to use the inverse transform function on our Y matrix, and that is something that we could in fact do. So we can use that PCA object, use the inverse transform function on our 16-dimensional principal components, or in other words, our 16-dimensional representation of each of the observations in our data set, and add that mean list back to that representation. Then essentially what we've given ourselves is now a 64-dimensional representation of our original MNIST matrix, MNIST matrix that has only preserved the information that was collected in those first 16 principal components. So we might be curious to see, well, how well did using just the first 16 principal components actually preserve the original, the original images of this data set here? So we can take that Y reduced representation of, let's just say, the first 10 images in the data set, and then we can compare that to what our original first 10 images in the data set looks like. Okay. And so for the most part, by simply just using 16 principal components to represent our original 64-dimensional data set, and then by projecting those 16-dimensional principal components back into a 64-dimensional space, we can see that for the most part, the actual image, or that each of these objects are a picture of, was pretty well preserved, right? We can still determine that this is in fact a 9, this is in fact an 8. Now, if we compare this to the original images, we do see that they the images themselves or the digits themselves are a little bit less crisp. So it's not a perfect reconstruction. But yeah, for the most part, we might say, well, this is enough for us to, determine what this is an image of. So we might say, well, yeah, 16 principal components might be an adequate amount of dimensions to represent our original data set, such that we're still actually preserving, the main important elements of what this is actually an image of, essentially. Okay. And so furthermore, we wanted to extract some additional insights from our principal component analysis that we just conducted. We can use the explained variance ratio. And what this extracts for us is each of the eigenvalues that we had calculated above. This is the percent. It's basically the ratio of the variance of the principal component with divided by the variance of the original attribute variances, or the original attribute variance sum. So basically what this is telling me is that the first principal component preserves, by itself, 14% of the original attribute variance. So this is telling me that the second principal component is preserving by itself 13% of the original attribute variance, so on and so forth. So by taking the sum of each of these variance ratios, this verifies that by using 16 principal components, that in total 84.9% of the original attribute variance is in fact preserved. Okay, all right, I'm doing a lot of talking. Any questions on that? Okay. Now, the main reason for why we're actually conducting this particular principal analysis is because we'd like to be able to quickly summarize the pixel relationships which are leading to the highest amount of variability in the data set. We'd like to explain the pixel relationships that are leading to the second highest amount of variability in the data set, so on and so forth. So to learn more about what vectors, i.e. pixel relationships, characterize this second highest, most amount of variability in the data set, we can explore what each of our loading vectors look like. So you want to remember our loading vectors matrix U is going to be comprised of 16 or P columns, but then each of these columns is actually has 64 dimensions or 64 rows. So what we can do is we can actually examine, or basically put each of those loading vectors back into an image representation. We can examine what it is we end up seeing when we visualize each of those loading vectors. Okay, so what I'm going to do here is I'm going to take my 64 loading vectors, which is this right here, excuse me, my 16 loading vectors. And in order to give myself a better visualization or a better representation, I want to remember that I had mean scaled my original data set ahead of time. So basically, I'm going to add back the mean of my original data set to each of these 16 loading vectors. Okay, so this is what I get here when I visualize that. So basically my first loading vector, the pixel relationship that characterizes the most amount of variance in the data set is characterized by this image here. And so furthermore, the pixel relationship, i.e. the loading vector that characterizes the second most amount of variance in my data set, is characterized by this image here, so on and so forth. So what we want to remember about basically how images are represented in Python is that darker values reflect, higher negative values, or basically the lower values in the range of observations that you're looking at, and then the lighter values represent higher values, if you will. So basically, these loading vectors are going to be comprised of both positive and negative values. So essentially, what you can interpret is that the darker values represent, high negative values, and the lighter values in this case represent high positive values. So what this tells me, or what this shows me, is that there's going to be some observations which, when projected onto this first loading vector, some of these observations will advance very far in that direction. Or in other words, what that means is that this particular pixel relationship, or this particular attribute relationship that is characterized by this first loading vector, what that is going to show me is that these particular observations are going to reflect the pixel relationships, or they're going to be characterized by the pixel relationships that we end up seeing here. So for instance, what we end up seeing is like in white is sort of this bend that exists in the digits. So what that might indicate is that observations that advance very far in the positive direction along this particular loading vector, i.e. observations that have a very high positive principal component 1 value, might be characterized by having this particular value, or this particular pixel relationship. So basically having a set of pixels that look like this in white. So this might suggest that, those observations with high positive principal component 1 values might be those that, have this element here. So they could be something like a 4, or maybe something like a 3, right? Because we know that a 4 has that, this little bend on the left-hand side there. Maybe a 6 as well. Okay. Now, alternatively, there could be observations in this data set that will, when we project them onto the first loading vector, they will end up having a high negative principal component 1 value. In other words, they will advance far along this loading vector, but in the positive direction. So what that might mean, or what that might suggest, is that those observations are characterized by having like white values, in these parts of the image. So essentially, when we are representing a image data set with a set of principal components, essentially what these loading vectors represent is it defines like a spectrum, if you will, or a spectrum that characterizes a particular pixel relationship, which is going to be capturing the highest amount of variance that exists in the data set. Now, similarly, we can inspect the second loading vector for information about, what pixel relationship characterizes the second highest amount of variance that exists in this data set. So, for instance, if an observation advances very far along this second loading vector in the positive direction, then what that means is that observation is likely to be highly characterized, or basically highly characterized by, the direction that this particular loading vector is going in. So in particular, what this might mean is, so for instance, if a given observation has a high corresponding positive principal component 2 value, then what that might suggest is that observation will have like white values in the same places that we're seeing white values here. So what that might suggest is that observations with high principal component, or high positive principal components 2 values, might be those that are, the 0 digits. On the other hand, observations that advance very far in the negative direction along that second loading vector, i.e. those observations that have a high negative principal component 2 value, might be more characterized by having values, or white values, if you will, that show up, around here. So this could be, for instance, images that might be 1, for instance, or other images that tend to have this white value here in the center. So essentially what we're describing here, or what we're showcasing, is that the pixel relationships that characterize the, the highest amount of variance that exists in this data set is based on whether or not the image has this bend here. And then the pixel relationships that describe the second highest amount of attribute variance that exists in the data set is going to be based on, whether or not they essentially have a hole, or whether or not they have, something that, observations that sort of like fill that hole, if you will. Okay, and we can keep this going. So if we wanted to examine the pixel relationship that, characterizes the third most amount of variance, then we can see that it might be defined by, sets of pixels that have like white values right here, or pixels that have white values right here if they're, if they have negative principal component 3 values, if you will. Okay, so this is one way that we might interpret the loading vectors as determining or indicating, what pixel relationships capture the most, second most, third most amount of variance in the data set. Okay, questions on that? Okay, let's see here. So so we can also, use the corresponding principal component values for each of the observations in our data set to, like we said, summarize or quickly summarize what that particular observation might be about, or in other words, evaluate the extent to which that particular observation is characterized by the loading vector relationships that we observed when we visualized those loading vectors. So for instance, what I might do here is I might decide to, for instance, plot just the first 2 principal component values for all of the observations in my data set. And I might choose to color code these observations by essentially what the image is actually a picture of. And so let's see if my assumptions or my interpretations that I collected or that I got from my loading vectors actually map on to what we're actually observing here in these corresponding principal component values. So for instance, what I can see here is that some of the observations that have the highest positive principal component 1 values are the images of a 4. And that's exactly what we suggested about, what loading vector 1 is actually telling us about the corresponding principal component 1 values. So we said that, observations that advance very far along loading vector 1 in the positive direction are likely to be those that are characterized by this particular pixel relationship, or in other words, those that have a set of white pixels, particularly around this area here. And that is in fact what we end up seeing with the 4 digits. And then alternatively, what we see here, it's not as immediately obvious, but it's not purely characterized by like 1 and only 1 digit. But what we end up seeing here is, for instance, the 3 or observations that are an image of the number 3 tend to have some of the highest negative principal component 1 values. And that does tend to map on with what we suggested here as well. So we said that, observations that advance in the, far along in the negative direction of this particular loading vector will look more like this pixel relationship described, where they're more likely to have these white images that we end up seeing here. So that is something that we tend to see in like the 3 and the 9 images. So we do end up seeing like a 3 will have, white values like here, here, and here. Okay, so basically what this is telling me is that the distinction between having this kind of bend versus having these kind of pixel values is in fact the relationship that characterizes the most amount of variance in the data set. And then furthermore, we can, explore what we're seeing here in the second principal component, right? And so, we can see that the 0 digits tend to be those with the highest positive principal component 2 values. And that's exactly what we were suggesting or interpreting from our corresponding loading vector 2. Or in other words, those observations that advance very far in the positive direction along loading vector 2 are going to be highly characterized by essentially having white parts of the images like around here and here, which is what we see in a 0. Okay, and then similarly, those observations with high negative principal component 2 values might be those that advance very far along the loading vector 2 in the negative direction, i.e. Those that are going to have or exhibit this type of pixel relationship. Okay, and so that would be things that we would end up expecting to see in like 7 images or 7 digits and 1 digits when we have like, something that looks like this. Okay, so basically what this further validates for us is that the pixel relationship that characterizes the second most amount of variability that exists in this data set is essentially whether or not the image has a hole versus, some sort of, thing in the middle of the image of the picture, if you will. Okay. And so furthermore, there's some observations which don't really have any, high positive or negative principal component 1 or principal component 2 values. So essentially you can interpret those observations as simply just not being characterized by those particular loading vectors. So in other words, they don't advance very far, in any direction along those 2 particular loading vectors. So that might say that, the remaining digits, these ones in the middle, these particular pixel relationships that we're, showing here aren't as salient when it comes to defining them, essentially. Okay. Oh, I'm out of breath. Any questions on that? Okay. Sorry, guys. I'm getting over a cold here, so I might be a little bit stuffy. But yeah, so if we wanted to kind of keep this process going, if we, if we wanted to learn a little bit more maybe about that, the third loading vector, or basically the pixel relationship that characterizes the third most amount of variance, then we could furthermore, plot, the relationship between, let's just say, principal component 1 and, now principal component 3. And so furthermore, we can see that, some of the observations which have the highest positive principal component 3 values are going to be those that advance very far in the positive direction along loading vector 2. So what that might suggest to us is that it's going to be those observations that are characterized by having something like this in their image. And we can in fact see that, a 2 does in fact have this component here in its image. Okay, so on and so forth. Okay, so I think that's all I wanted to say about that. Yeah, so basically that concludes our analysis of principal component analysis. You can use this for a wide variety of other applications as well. So like I mentioned, if you have a features matrix and you'd like to get rid of multicollinearity, you can take your features matrix, project it onto a certain subset of principal components, and then essentially preserve that original attribute variance while getting rid of the multicollinearity issue. But as we've discussed here, that's you can also learn really interesting insights about what's going on in your data set for unsupervised learning purposes as well. Okay. All right, so any questions on that? Okay, so I guess with the last 16 minutes, we'll move on to non-negative matrix factorization. Okay. And so like I mentioned, so non-negative matrix factorization is actually, yeah, it's one of my favorite clustering algorithms, I would say, because it's actually it serves a lot of different purposes and it has a lot of functions. So it actually combines a lot of the things that we've been talking about with a lot of the clustering algorithms and dimensionality reductions algorithms that we've talked about so far. And it kind of does all of them at once, essentially. So we're going to talk about all the cool things that the non-negative matrix factorization can do. But first, we want to remember that a non-negative matrix factorization, it can essentially be used as a dimensionality reduction algorithm as well as a clustering algorithm. So we first might ask, so we want to give a little bit of a backstory as to why the non-negative matrix factorization algorithm was, created in the first place. So before the NMF algorithm was created, we had the principal component analysis. So we had this way essentially of, taking this high dimensional data set, projecting it onto a low dimensional data set, and preserving some aspect of the original data set, or more specifically, the original attribute variance. So what some people were tempted to do was they were essentially tempted to try to essentially take this Y matrix, our, let's just say 3 projected principal components, and they were tempted to, they were asking ourselves, well, wouldn't it be great if we can actually take this, a lower dimensional representation, and somehow try to interpret it as a fuzzy clustering membership matrix? So we can see here that, the Y matrix by itself, certainly does not represent what we might expect for a fuzzy clustering membership matrix, right? So number one, the key thing or the key property that a fuzzy clustering membership matrix needs to satisfy is that, the sum of the rows should add up to 1, number one. Number two, you're not meant to have any like negative values. So essentially a row in a fuzzy clustering membership matrix should look like a probability distribution. Or in other words, it allows for you to, reflect the extent to which a given observation corresponds to a given cluster. So basically each of these observations in a given row should reflect a percentage, and these rows should add up to 1. So nonetheless, some people were tempted to, try to take this principal component matrix and try to manipulate it such that, the properties of a fuzzy clustering membership matrix were in fact actually met. So first we want to think about, actually, I think I might skip over this part here. So we might want to think about, why is this approach not necessarily going to be the most insightful when it comes to a cluster analysis? Or in other words, why should we not use principal component analysis to try to cluster our data sets? Okay, so let's talk about some of the issues that we first experienced with principal component analysis. So one issue is we want to think about, well, what did we have to do to our X matrix in order for us to use PCA? So the question is, are we allowed to use principal component analysis for all types of matrices, or do we have to transform the matrix first? And if so, yeah, exactly. So in order to use PCA, one potential downside is that, we had to mean scale the X matrix first. Okay. Now another pitfall, if we were to attempt to try to use PCA to cluster a data set, is we want to think about, well, what does PCA, what is PCA actually trying to preserve? So we've discussed this thoroughly. We want to remember that PCA is not designed to preserve the clustering structure of the given data set. It's designed to preserve the sum of the original attribute variances. Okay, so key thing that you want to remember is by representing your original matrix X with P principal components, it's possible that your original clustering structure could weaken or disappear altogether. Okay, but nonetheless, let's just say we were still tempted nonetheless to try to force this principal component, or basically force the principal components to somehow reflect a fuzzy clustering membership matrix. So we want to ask ourselves, is there a straightforward way to do this? So is it possible for us to somehow manipulate this matrix in some particular way such that we could create essentially, so such that we could actually force each of the rows in our principal component projection to essentially look like a probability distribution? So basically, is there a straightforward way mathematically to force each of our given rows to look like a probability distribution? Yeah, well, so here's the thing. So for some of these rows, you could get lucky, right? So for instance, let's just say this row here, it just so happened that all of my observations were non-negative. So if I was guaranteed this property for my principal components, that all of my observations in a given row were non-negative, then something that I could do to basically force this probability distribution property might be to simply just take the sum of a given row and then just divide each of those observations by that row sum. Okay, and in so doing, at least for this particular row, it would force that, the set or that particular row to be a probability distribution. Or in other words, each of these observations are constrained to be between 0 and 1, and the sum of the observations in the row will add up to 1. Okay. However, we run into a problem here, and this is the main problem, or well, one of many problems that we would, practically speaking, run into if we were to try to force the principal component matrix to represent a fuzzy clustering membership matrix. So unfortunately, we are never guaranteed to get a principal component matrix in which all of the observations are non-negative. So this begs the question, what are we supposed to do if we end up getting a row with non-negative values? Okay. So if the principal component matrix Y was guaranteed to be non-negative, then we could convert Y into a fuzzy clustering membership matrix by dividing each value in the row, by its corresponding row sum. However, a principal component matrix Y is never guaranteed to be completely non-negative. So when a row has negative values, it is not, there's not a straightforward way. Sensibly convert a row, that given row, into a fuzzy clustering of the given observation. Okay. So this is why we're going to introduce non-negative matrix factorization, which, as the name suggests, gives us this, p-dimensional representation of our original data set in which all of the observations are forced to be non-negative. So by forcing all those observations to be non-negative in this new representation, which we're going to call our W matrix, then we can, in fact, actually convert each of the rows into a probability distribution. Or in other words, we can, in so doing, turn our resulting W matrix representation of our original data set into a fuzzy clustering membership matrix. Okay, so this is going to be one of the benefits that non-negative matrix factorization has. And this is kind of giving a little bit of the history as to how and why it was created. So it's based on some of the shortcomings of the principal component analysis. And then I want to talk about some other drawbacks of the clustering algorithms that we've talked about so far. So for instance, we have our TripAdvisor data set, which has 980 people or observations. And each of these people or observations corresponds to 10 different, trip attributes, if you will. So, up until this point, our goal was to cluster the 980 people based on their 10 trip type preferences. But then let's just assume, for instance, rather than clustering the people, what if we actually wanted to consider our observations to be the 10 attributes, and we wanted to basically consider their attributes to be the preferences of the 980 people. In other words, what if we wanted to cluster the 10 trip types based on the preferences of the 980 people? So how might we go about doing that? Using one of the clustering algorithms that we've discussed in the past. So for instance, if this was simply just my X matrix here, what I might have done in Python, right, is for instance, I might have chosen to cluster X into, let's just say, 3 clusters. So, this code would have, pursued this goal for me. So what could I do if I wanted to perform this other analysis in which I was clustering the 10 trip types? Any ideas? So could I just take the X matrix and transpose it? Yeah. Okay. So, I mean, there's nothing really special about, what we have, indicated to be the rows or the columns of our matrix that we're clustering, right? So, Python presumes, whatever you have on the rows in your input matrix for, a lot of the clustering algorithms that we've talked about, it presumes those to be the observations that you'd like to cluster. And then the columns, it presumes that to be the corresponding attributes of those observations. So, if I wanted to cluster the 10 trips and have the 980 people represent the attributes, then all I need to do is transpose that that X matrix, if you will. But that's certainly something that I could do. But something that none of these clustering algorithms that we've discussed so far have the ability to cluster both the observation, say cluster both the rows and the columns of our X matrix at the same time. Okay. That's actually going to be one of the benefits of our non-negative matrix factorization, in that it relies upon, or basically it clusters both the rows and the columns of a given matrix at the same time. So basically, we're relying on information that both of these rows and columns are essentially saying about each other at the same time. So we're not essentially, if we were to cluster, just the rows or cluster just the columns in two separate algorithms, it's possible that we might be missing out on relevant information, or in other words, we might be losing information that can tell us more about the interlocking relationships between the rows and the columns. Okay. All right, cool. So I've run out of time. So I think, yeah. All right, so I think we'll wrap there. Yeah, so I have office hours tomorrow. So if you have any questions, feel free to drop by. We'll stop recording.